Assalamu alaikum warahmatullahi wabarakatuh. Today is our lecture 30, and in this lecture, we will continue our chapter 5. And today's topic is expected value of a function of two random variables. So, as we have seen for the first one random variable, that we can define a function and we can also find their expected value and the all the other things PMF and PDF. So similarly, here we have the function gxy, a function of two random variables, a function of two random variables, and it is also known as is also a random variable. It is convenient to calculate the expected value, that is expected value of gxy, without deriving a probability model of gxy. So the expected value for a random variables, so we can say that the expected value for the random variables x and y, and it can be calculated as it is defined as theorem 5.9. So it says that for random variables x and y, the expected value of w is equal to gxy is, now it is defined both for discrete and continuous. So for discrete, we can say that we can say that expected value of w is summation over x, or range of x, summation over range of y, g xy, p joint PMF of xy. Similarly, for the continuous, expected value of w can be defined as double integral over the range of x and y, gxy, times the joint PDF of x and y. So this is very convenient, and it also leads to a very interesting another theorem. So it actually lets us calculate easily the expected value of a linear combination of several functions. So this is defined as the extension as the theorem 5.10, and it says that the expected value of a1 g1 xy plus up to an gn x y can be find out by writing their expected values as the sum of their individual expected values. Xy plus up to plus an expected value of gn xy. So that is for the n number of functions. If we have n functions of x and y, so we can find out their expected value easily because of this theorem. Now we can reduce this theorem to a special case of only two random variables. So theorem 5.11, and it is the expected value of the sum of two random variables, and that can be treated as a special case of theorem 5.10. And so it says that for any two random variables x and y, expected value of x plus y is equal to expected value of x plus expected value of y. So that is very convenient. Now next we have actually these are just basic definitions, so don't worry about that I'm writing too much theorems here. So they are simple. 5.12, and it says that the variance, as we know that the variance is defined as the spread of the data. Now we have seen for the single random variable. Now we will see the variance of the sum of two random variables is variance of x plus y, which is equal to variance of x plus variance of y plus 2 times expected value of x minus mu x into y minus mu y. So that whole is defined as the variance of sum of the two random variables. So here we can see that if we know the variance of x and variance of y, and if we calculate this this big term, expected value of x minus mu x into y minus mu y, which actually is known as the another important parameter in data analysis, in this analysis of these random variables, is the covariance. So we will define these terms separately, as we have covariance, correlation, and independence. So we can say that the covariance, first we define the covariance. So the covariance is defined as, we write it as covariance of xy as COV xy, which is equal to expected value of x minus mu x into y minus mu y. So we can actually we can infer from here that what actually it means, what it will let us know that just like the expected value tells us the central tendency or the middle values or the mean of the random variable. Now the covariance, what it will tell us. So because here we have two variables, so we have three conditions for the covariance. So the first condition is, or we can write it as the conditions for covariance of xy. So it means that for first condition, we say that if covariance of xy is greater than 0, means it's a strictly positive value. So it is a positive value. So what it says that it simply means that x minus mu x and y minus mu y have the same sign, have the same sign, means both could be positive positive or both could be negative negative. So in this case we know that what will happen that uh, uh, so what we would expect from here that if 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 x goes up, if x goes up or down, y will be the we having the same behavior. Y will also go up or down. So similarly, we can have the second case. In the second case, uh, we can see that the covariance of xy is less than 0, means it's strictly negative. So for it to be negative, it simply means that x minus mu x and y minus mu y have different signs, have different sign, means it could be plus minus minus plus. So in that case we can infer from here that uh, if if x goes up, y typically goes down, means they behave in opposite direction, they will behave in opposite direction. So finally, the third case is that if covariance of xy is approximately or is equal to 0, so what it means that it simply means that the sign of x minus mu x does not provide much of the clue about the sign of y minus mu y. So there is another issue, just like we have seen with the variance, that we get the units squared. So means if some value is very close to 0, means if somebody says covariance of xy is approximately say 0.1, so whether it could be taken as approximately equal to 0 or not, so it actually depends upon the units. So we have to, if we are working with the covariance, so we have to be very careful about the units. So to avoid this thing, we actually have another parameter which we call it as the correlation correlation coefficient. The correlation coefficient is a unitless because it's a ratio, so it has no units. So it is defined as the rho xy is equal to, it is defined as covariance of xy, and we divide it with the square root of variance of x and variance of y. So obviously it will have the unit square. So its variance is also has the unit square, unit square. So that square units will cancel out with the square root, and we will cancel out their units with this covariance units of covariance of xy. So we can write it as covariance of xy as the sigma x sigma y, which is the standard deviation. So this is a unitless and that will dimensionless quantity that is not affected by the scale change. So we have certain more properties of these uh, uh, covariance and the correlation coefficient. So that is defined as the theorem 5.13. So theorem 5.13 says that if we call it, say, x hat is equal to ax plus b, just had to show that this is some other random variable, and y hat is equal to c y plus d, then row of x hat y hat will be same as the row correlation coefficient of xy. Similarly, the uh, covariance of x hat y hat will be equal to ac, these constants, times product of their constant times the covariance of x y, because b and d are the constants and their spread is not a meaningful value. So there is a again I will say sorry for these too much theorems, but they are just basic definitions. So there is another theorem which defines the range of this correlation coefficient, and it says that rho of xy base should be between -1 and 1. So that should be between -1 and 1. So so we can also infer from here that how these are. So we say that case 1. So we say that rho of xy is greater than 0. So it simply means that x and y are positively correlated, positively positively correlated, positively correlated. Okay, and when we say that case 2 rho of xy is less than 0, so we say that x and y are negatively correlated. So correlated simply means that they are interlinked with each other, how much they have impact on each other. So if we say that case 3 case 3 that the magnitude of rho xy is close to 1, say approximately say 0.9, so we say that x and y are highly correlated, correlated highly correlated. So this can be visualized in the graphical form. It says that it is the each graph has 200 samples, each marked by a dot of the random variable pair xy, such that expected value of x is equal to expected value of y is equal to 0, and the variance of x is equal to variance of y, which is equal to 1. So if their correlation is negative, so we can see that this kind of pattern in the, and if there is no correlation, so everything is scattered in the whole range of this data set. But if it is a positive and close to 1, so we can see that they have the linear relationship among the between the x and y. So we have another theorem to define another property of this 5.15, and it says that if x and y are random variables such that y is equal to ax plus b, then the correlation coefficient then the correlation coefficient xy, rho xy, will be such -1, 0, 1, and it would be -1 when a is less than 0, and if a is equal to 0, correlation coefficient would be 0, and it is +1 if a is greater than 0. So there is another terminology, or we can have some examples of this to show that how it is, just like x, if x is the student's height and y is the same student's weight, so rho will be between the 0 and 1, so these correlation coefficient will be between 0 and 1. Similarly, if x is the temperature of the resistor measured in degrees Celsius, then y is the temperature of the same resistor measured in kelvins, so that their correlation would be 1. So rho x will be 1. Similarly, if x is the distance of the cellular phone from the nearest base station, y is the power of the received signal at the cellular phone, then rho of x will be between -1 to 0. Similarly, so we can have different examples to show that how two random variables are interlinked with each other, and whether the correlation coefficient would be positive or negative depending upon the system that we have. So I have copied these some of the examples from the book, that x is a student's height, y is the same student's weight. So we can see that the correlation coefficient will be between 0 and 1, and similarly all these different examples that we have here to describe how these correlation correlation coefficient of two random variables is defined for different scenarios. Now the next terminology that we have to see is the correlation. Correlation itself. So correlation is defined as the Rxy, which is equal to expected value of the product of xy, the product of xy. So we can define another theorem to define the certain properties. So it is actually theorem 5.16. So it says that the covariance of xy can be written as Rxy minus mu x mu y. Similarly, the second property, variance of x plus y, can be written as variance of x plus variance of y plus 2 times covariance of x, y. And C says that if x is equal to y, means both are the same, then covariance of xy will be equal to variance of x, which is equal to variance of y, and their correlation will be simply the second moment will be the second moment. So let's look at an example to understand some of these concepts that we have seen. These are simple concepts, but they are very useful concepts that we are used very much in your practical life. So let's have an example. Sorry. So I've got this example from the book. So it is example 5.17. It says that the for integrated circuit test in example 5.3, we found in example 5.5 that the probability model for x and y is given by the following matrix. So we have this, we have made this matrix or table already, and we have to find the correlation and the covariance of this data of these random variables x and y. So let's start. So first we need to calculate this correlation, which is equal to expected value of xy, which should be summation of x equal to 0 to x is from 0 to 2, and summation y is equal to 0 to 2 x product of xy px y joint pmf. Now we will take this, we will remove the 0 0 values wherever it comes. So rest of the remaining of the values will be simply 1 1 into 0 0.09 and plus 2 2 into 0.81. So rest of the values are either here, these are zeros, or this 0 0. So we will remove all those values. So we will get only these two values, which is 1 1 and 2 2. All other values have at least one value of them is 0. So this will be 0 0.09, or it will be sum up to total 3.33. Now we have to calculate the covariance of xy. So to find the covariance of xy, we can use the last theorem 5.16, the first part, which says that the covariance of x is covariance of xy is equal to correlation minus product of their product of their expected values. So we can easily calculate the expected value of x, which is already clear from the table that it would be 1 into 0.18 plus 2 into 0.81, which is equal to 1.80. Similarly, we can calculate the expected value of y, which is 1 into 0.09. I hope I don't have to do each and every step for these basic things. We have already done it thoroughly. So 1.71. So covariance of xy would be then what we have correlation as 3.33 minus 1.80 into 1.71. So it is 0.252. Now there are another important definitions that we must be careful about. One is known as the orthogonal random variables. Orthogonal random variables. We have already seen that what the orthogonal vectors means. Orthogonal vectors means they are at 90 degree and they have nothing in common in between them. Means one vector have no projection on the another vector. So we say that these two vectors are orthogonal. So in random variables, so we say therefore the random variables are random variables x and y are x and y are orthogonal if their correlation is 0. Similarly, there is another terminology which says that the uncorrelated uncorre uh, uncorrelated random variables. So for random variables to be random variables are random variables x and y are uncorrelated if their covariance is 0. So don't get confused with these two terminologies. Always remember that the orthogonal means their correlation is 0 and uncorrelated means they have 0 covariance. So kindly remember this thing, that once again, if two random variables their correlation is 0, we say that they are orthogonal, and if two random variables their covariance is 0, we say that they are uncorrelated functions. So here we have some more properties which are defined as theorem 5.17. So it says that for the independence of the two random variables, we say that for independent random variables x and y, we have expected value of g of x, h of y, which is equal to expected value of their separate product of their separate expected values if they are independent, just like we have seen already. So similarly, if two x and y are independent, then their correlation will be simply equal to expected value of x into expected value of y. So similarly, the covariance of two independent random variables, so their correlation coefficient would be 0. So their correlation coefficient would be 0, and the variance of two random variables will be simply the variance of x plus variance of y, since the correlation plus 2 COV, which is already 0. So let's look at an example. So it is quiz 5.8a. It's for the discrete random variable. So we have been given this uh, joint PMF. So again we will do this summation to find out this would be our uh, marginal PMF of L, and here we will have the marginal PMF of T. So it will be 0.25 and 0.5, 0.25. Here it would be 0.6 and 0.4. Now it says that find the expected value of L and variance of L. So that is expected value of L. We know that that's the summation of x times PMF of L. So that will be 1 into 0.25 plus 2 into 0.5 plus 3 into 0.25. So this sums up to be 2. And the variance of L, for that we need to calculate the second moment L square. So that will be 1 square 0.25 plus 2 square 0.5 plus 3 square into 0.25, and that comes out to be 4.5. So variance of L then will be so that is equal to L square second moment minus first moment. So that is 4.5 minus 2, which is 2.5. So sorry, it is 4 because it is square, so this would be 0.5. Similarly, for the second part, expected value of T will be equal to 40 into 0.6 plus 60 into 0.4, which comes out to be 48, and second moment will be 40 square into 0.6 plus 60 square into 0.4, which will come out to be 2400, and the variance of T will be simply x second moment minus square of the first moment. So that would be equal to 96. Similarly, then the third part says that we have to find the covariance of LT, covariance, covariance of LT. So for that, we have this expected value of LT correlation minus product of their individual probabilities. So we need to find out this correlation first. So that would be simply summation T is equal to 40, 60, and for L is equal to 1 to 3 LT and their joint PMF. So that would be simply 1 into 40, 0.15, 2 into 40, 0.3, plus 3 into 40, 0.15. Similarly, we have 1 into 60, 0.1, plus 2 into 60, 0.2, plus 3 into 60, 0.1. So this will sum up to be 96. So then covariance will be simply 96 minus 2 into 48, which is 0. So covariance of this is 0. So the D part says that we need to calculate the correlation coefficient. So we need to find out the correlation coefficient, which is rho LT. As covariance is 0, so covariance divided by something, whatever it is, so that would be 0. The second, this problem has a second part, and the second part is for the continuous random variable. So we have been given the joint PDF of a random variables x and y has this one. So we have to find the expected value of x and variance of x and all those parameters that we have done for part A. So that's again quite easy, but for the continuous random variables, first we need to find out their marginal PDFs. So the marginal, first of all, we need to find out their marginal PDFs, fx of x. So that is the minus integral, minus infinity to infinity integral of joint PDF over y. So that will be 0 to 2 xy dy, which is 1 over 2 xy square for y is equal to 0 to 0 to 2. So this will come out to be 2x. So we can say that f of x is 2x for x is between 1 and 0, 0 otherwise. Similarly, fy of y will be y over 2 to 0 for y between 2 and 0. So I hope you can find it similarly by integrating over x. Now we can move for the first part, which is the expected value of x. So which is minus infinity to infinity x fx of x dx. So it is 0 to 1 2x square dx, which comes out to be 2 by 3. And to find the variance, we need to find the second moment. So that would be minus infinity to infinity x square fx of x dx, which is 0 to 1 2x cube dx, which is 1 over 2. So variance of x then will be expected value of x square minus expected value of x square, which comes out to be 1 over 18. Similarly, the second part says that find the expected value of y. So expected value of y will be the minus infinity to infinity y fy of y dy, which is equal to 0 to 2 1 over 2 y square dy, and this integral will come up with equal to 4 by 3. Similarly, to find the variance, we need to calculate this second moment, minus infinity to infinity y square fy of y dy, which is 0 to 2 1 over 2 y cube dy, and this integral will be 2. So variance of y then will be equal to second moment minus square of the first moment. So that would be simply 2 by 9. Now we need to find the correlation. We need to find the covariance of x and y. C parts covariance of xy. So covariance of xy, as we know that, which is equal to the expected value of this xy, which is the correlation, minus mu x mu y. So we have this mu x and mu y, so we need to calculate this xy. So that will be the integral minus infinity to infinity minus infinity to infinity xy fxy dx dy. So this will be 0 to 1, 0 to 2 x square y square dx dy, so which comes out to be x3 by 3, 0 to 1 y3 by 3, 0 to 2, so it would be 8 over 9. So covariance will be then this correlation minus expected value of x. So this is 8 over 9 minus 2 over 3 into 4 over 3, so which is 0. So similarly, the last part, it says that find the correlation coefficient. So correlation coefficient is actually, we know that it is covariance of xy divided by standard deviation of x, standard deviation of y. So this is 0. So I hope you have understood all these, and we will continue in our next lecture. So stay blessed. Assalamu alaikum wa rahmatullahi wa barakatuh.